Very happy to introduce Kate today. Kate is going to talk to us about honeybees and how honey can be used as a mechanism for environmental surveillance. So Kate holds a BSc in chemistry from Michigan Technological University and a master's in geochemistry from the University of Wisconsin-Madison. She worked as an environmental chemist in the state of Wisconsin for 7 years, first in chemistry and toxicology for veterinary diagnostics, and then in the Trace Element Clean Lab research group at Wisconsin State Laboratory of Hygiene. Kate's currently in the 4th year of her PhD in the UBC Earth, Ocean, and Atmospheric Sciences Department, and her research interests fall at the intersection of urban geochemistry, environmental health, and public health. Kate's just finishing up her doctoral project exploring the use of honey as a biomonitor for metals in cities, and she'll be sharing some results of her doctoral research with us today. So welcome, Kate, and please go ahead and unmute.
All right. Thank you so much, Sarah. And thank you all for logging in and joining me today. Too bad we can't be here in person, but we'll make do. Okay, first of all, I hope you can see my pointer. And then we'll get started.
We can. It's a nice big red dot.
Okay, good. I am really interested in this emerging subdiscipline of environmental geochemistry that we're calling urban geochemistry. And we know that for most humans, cities are a natural environment. That's where humans reside. And I think it was 2014, which was the official tipping point where officially more than every 1 in 2 humans live in a city. And I think the projection is by 2050 or 2060, it's going to be more than 2/3 of all humans are going to be in an urban environment. But cities also have a profound environmental impact, and that was true in ancient cities, but it's especially true since the Industrial Revolution. And in order to properly assess and monitor that impact that cities have on the environment we have to recognize that the timescales are rapid. And this is a little bit challenging sometimes for geochemists to wrap their head around.
They send a link.
Hang on a second here. Somebody is not on mute. Please, everybody take care to mute your microphones, and I'll just scan through the list here to see if I can find who that is. Okay, I think we're good to go. So sorry about that, Kate. Go ahead.
Okay, no problem. All the fun of technical presentations, huh? So the thing that geochemists have to remember is that the timescales are rapid in terms of what they're used to thinking about. The processes and biogeochemical cycling that they're used to thinking about are expedited in a city, because a city is the perfect example of this confluence of many point sources all in a small footprint, and loads of other processes in a small footprint, all a culmination of all critical zone activities in one place. And so it's also a truly interdisciplinary field. So we have to require collaboration from fields of environmental and geoscience, of course, engineering, public health, public policy, and really importantly, the community. So I'm an inorganic chemist. I'm really interested in how metals move through urban environments, so sources, transport processes, and sinks. But today we're going to focus on lead for 2 reasons. Lead, of course, is neurotoxic. The legacy of lead pollution still haunts us today and will for centuries, I'm sure. It's a huge public health issue, and especially in cities, you have concentrated amounts of lead in various matrices for a number of reasons. And the second reason is that lead is incredibly useful from a geochemical standpoint because of its stable isotopes. It's really useful for helping us pinpoint different sources of lead in a given material. So I'll mention the use of biomonitors today. And you are all familiar, I think, with the classic example of a bioindicator, which is the canary in the coal mine. The canary dies, and that gives you some qualitative information about the environment that you're in. So it tells you that you've reached a level of carbon monoxide, for example, that's going to kill the canary. A biomonitor, at least in the definition that we're going to use today, is a living thing that gives you some quantitative, some measurable feedback about the environment that it's in. And so ideally you would want something that has a huge local population density, so not a rare species. You want something that's commonly distributed within your area of surveillance. You want something that's pretty simple, cheap to survey, ecologically useful, and it helps if there's some public interest in your species that you select. That helps for funding and also outreach and public awareness of the work. And honeybees actually meet all of those criteria. And what's really nice about honeybees is they're actively foraging for their pollen and their nectar, but as they do so, they also passively collect loads of particulate matter as they fly through the air, as they land on topsoil, as they drink surface water, and land on any other anthropogenic surfaces too. So they bring all this material that they both actively and passively collected back to their hive, and the tissue, the bees themselves, and the materials that they produce, so hive products like honey, wax, bee pollen, all reflect an extremely localized geochemical snapshot of the hive's immediate environment. So there's this sort of built-in geospatial context with the data that the bees provide. And it's really nice in a city like Vancouver, which has amazing greening initiatives, a lot of green space. In general, gardeners are pretty well aware of what pollinator-friendly plants to produce. The bees don't have to go far to forage. So we're really just thinking about a few kilometers is more than enough for them to forage. And a healthy hive can have up to tens of thousands of foragers. And so it's truly a crowdsourced sampling mechanism. So we have this really unique opportunity to work with a local nonprofit group called Hives for Humanity. They manage altogether several hundred hives all across Metro Vancouver. In particular, they do a lot of work with communities on the downtown east side. And if you're interested in honey at all and you want to support a local community organization, their honey is excellent. It's really, really good. And it's a cool organization. But I'm just curious, this brings us to our first poll question. I'm curious if you have any idea how many honeybee hives currently exist in Metro Vancouver. And so this is more than just City of Vancouver. This is the entire metro area.
We usually try to wait till we hit about 80%. Oh, wow, we've just got answers flying.
That was fast. You guys are speedy today.
Maybe we can hit a record of 100%. I'll give it a couple more seconds. 98. Okay, that's remarkable.
That's pretty good.
And then I will share the results so that everybody can see them for a little bit. And then stop sharing, and you may have to clear that window from your screen.
Okay, definitely. Okay, so that's actually a really good guess. You guys guessed between 1,000 and 10,000, but it's actually D. It's closer to 17,000 hives at any given time in Metro Vancouver. And so the source of this information is our very own provincial apiarist, Paul Van Westendorp. And he says this number is based on active hive registrations. They are livestock. You have to register the hives, but he thinks it's an underestimate because there are a lot of sort of under the radar hives around the city. So now that you know how many there are, you're going to start seeing them everywhere, I'm sure. So we did not sample 17,000 hives, but with the help of Hives for Humanity, we had access to a really, really nice selection of research hives located in all different types of land use. So we have hives in the downtown sector, the sort of central business, commercial, industrial core of the city, also medium density, mixed zoning, residential, suburban, and agricultural. And the most remote sampling site we had was on Galiano Island, which is mostly rural and agricultural land use. It's really good coverage. Just a few field photos for you. Here's some nice rooftop hives in the downtown core, some very beautiful hives in a very well manicured suburban backyard, and some hives down on a farm in Delta. So we would revisit most of these hives. I think we had at one point about 60 sites, but it varied from year to year. Over the course of 6 years, we could visit anywhere from 40 to 60 sites, and a lot of them were the exact same location, if not the same hive, which was really nice from a field sampling standpoint. And I was looking for bright white, freshly capped honey. When the bees produce honey, when the bees produce wax, it's actually bright white at first, and over time it'll oxidize and turn into that yellow or light brown wax that you're used to seeing. So as long as they're bright white caps, and as long as the honey is capped, that means it's ready for sampling. So the bees, they know when to cap the honey. That means it has the appropriate moisture content and the appropriate level of peroxide and a few key enzymes, and that's what makes honey shelf stable for eternity. In theory, honey is stable forever. So we're looking for capped honey from this season or the given sampling season, and that's what we were sampling. We also sampled bee pollen as well as foraging honeybees from each hive to compare various hive matrices and different efficacies of using those as biomonitors. But this talk today, we're going to mostly focus on honey. And honey is mostly, well, it's essentially a super saturated sugar solution. So it's mostly water, simple sugars, and a few complex sugars. And the parts that make honey interesting, that make it taste different, and that's mostly governed by the vegetation that the bees are sampling. It's really just makes up a very small percentage by mass of the chemistry of honey. But for me, I'm interested in this inorganic fraction, which can be as low as 0.02%. So we're talking about very, very, very low levels that we need clean labs to do the work. And over the years, I selected a suite of trace elements that are, they fall into several categories, both of interest biologically and geochemically. So we've got macro and micronutrients, as well as toxic metals that have no biological function for either bees or humans consuming the products, things like lead and cadmium. Geochemically, this suite of elements is interesting too, because it helps us trace both lithogenic or geogenic versus anthropogenic processes. And the organic fraction of honey is really useful too. This has been used for decades for tracking things like improper pesticide application, pharmaceutical residues, PCBs, PAHs, PBBs, and a lot of other persistent organic pollutants in various types of land use settings. But again, we're just interested in this inorganic fraction for this work, which is a bit of a challenge analytically because it's such low levels. So I did a full acid microwave digestion on the honey and the bees and the pollen. Basically, any matrix we were looking at required this pretty aggressive sample treatment. And then elemental concentration was analyzed by inductively coupled plasma mass spec. And then we used high-res ICP mass spec for the lead isotope work. And I have to reiterate, because we're talking about a food product and we're talking about lead, that I'm talking about very, very, very low levels. Such low levels, and we're talking about tens of parts per billion. And these levels are low enough that we have to be fighting against contamination all the time. So you can look at this photograph and see that there aren't nothing is made of metal. And everything, even down to the hardware and fixtures, everything is nylon or plastic, and all of the labware is made of Teflon. So you can't even wear your street shoes or your street clothes into this laboratory. There's actually a series of airlock rooms with various levels of air handling to keep the atmosphere so safe. No cosmetics, no dry shampoos. You can't even bring a cell phone into this lab because there's enough rare earth elements in this phone to throw off some of the analyses that my colleagues are doing. So the honey is safe to eat. The levels of lead we're dealing with are incredibly low. And all of the mass spectrometry we've done is done here at UBC at the Pacific Center for Isotopic and Geochemical Research. It's an amazing facility. I hope maybe post-pandemic you could come visit and have a lab tour because it's really something. And they do a lot of interesting environmental work. So hopefully some future collaborations are in the works. So here are some results from 6 years of honey data, about 250 analyses. And I've pulled a few trace elements that are really key for tracing anthropogenic activity. So zinc is in tire rubber. So a lot of stop and go traffic generates a lot of zinc. Titanium is on road paints, vanadium is in heavy fuel oils. And of course, all of these are in alloys. So weathering of civil structures, you get stormwater runoff. All of these things contribute to the movement of these metals through cities. And the trace element trends that we see in honey are consistent with the trends you'd expect to see in a city, the distribution patterns rather. And remember, this is our city center. We've got the massive industrial center here at the Port of Vancouver and shipbuilding activities in North Van. Just for those of you who aren't familiar with Vancouver. Oops. And we can look at this a little bit differently. So this is just a plot of concentrations as you move away from the city center. And you can see I pulled a few different metals here just to give you another example. We've got a bit of a bump here at Bowen Island. I think that's probably just really heavy ferry traffic through this corridor here. But in general, these metals that are associated with anthropogenic activity, industry, stop and go traffic, and legacy pollutants are more concentrated in the city center. And the fact that this comes through in honey, I thought was pretty exciting. So we have a more powerful tool that we can use to look at this data set, and that's the use of lead isotopes. And all you really have to understand is that because of these very different half-lives and very different decay chains of these different parent products, everything on Earth that contains some amount of lead has a characteristic composition of the various isotopes. And the differences are actually measurable, which is good news for us. This isotopic composition of any given material, whether it's a leaded gasoline or maybe it's an ore body that was mined to produce lead pipes or something, they all have a measurable isotopic composition. And this has been exploited for decades in environmental applications where they're trying to piece together where various sources of lead is coming from. And unfortunately, because of probably one of the biggest public health travesties of the 20th century, our modern day global lead isotopic mixing line is completely overwhelmed by the leaded gasoline mixing line. They're almost unresolvable. And the end members there are, of course, the Broken Hill ore mined in Australia and the Mississippi Valley type lead ore from southeast of Missouri in the United States. And all of other ores used to make the tetraethyl lead organolead additive were from the bulk of these two mines, but also from other mines that fall on a mixing line between those two end members. So this is a simple question, but I think it's really important that we go over this. A quick true or false question for the audience. So true or false, does today's unleaded gasoline contain any lead? We're getting really good turnout on these polls.
We are. People who are flagged as hosts cannot vote, but I'm voting false. I'll end this and share it.
Well, then those who voted with Sarah are correct. It's definitely false. Even though we're not adding any of these organo-lead additives, so tetraethyl lead, this compound was the most commonly added, and also some tetramethyl lead was added in a few parts of the world. There's still significant amounts of lead in gasoline. It depends, it's quite variable. It could be up to, well, significant in my mind as a chemist, up to several parts per million. And it depends on where the crude oil came from and the geologic setting and several other factors. But so keep that in mind. You guys know that vehicle exhaust is bad for your health for a number of reasons, but lead just makes it even worse. So we'll review a couple of sources of lead in Metro Vancouver. We have natural sources. We have natural erosional processes, basalt, andesite. We've got a lot of granite and andesite and things like that around us. Those all contain measurable amounts of lead. Whenever there's a forest fire in BC's interior or west coast south of us, particulates get dumped into Vancouver. We also have anthropogenic sources. And the wild card, this is our legacy pollution. The leaded gasoline and the leaded paint, once it's deposited in the environment, it's really hard to remediate, and it's not terribly mobile. Lead's very heavy, so it kind of sticks around, and it's a real headache. And of course, it's a huge public health issue when you have contaminated topsoil, especially in neighborhoods that have been previously used for industrial purposes or maybe repurposed brownfields. Lead in the soil is a huge issue. And I just want to point out that this is a completely dynamic system. So at any given time, these vectors, if they could even be called vectors, are the relative magnitudes could be completely different. And of course, it's not a closed system. I hope I don't imply that. So this is a 3-isotope plot. All you have to understand is a given sample is going to plot on this diagram. Where it plots on the diagram is going to tell us something about the different sources of lead contributing to its overall isotopic composition. And so in Vancouver, we find actually distinctly different isotopic compositions for honey collected in the downtown or the city core versus suburban and more rural honey. And to give you a bit of context, our local rocks plot down here, and our city honeys, the ones from the city center, the core of the city, plot up here, where they are seeing a little bit more input of more local anthropogenic sources and potentially sources from further away. And if we can plot this in map form, it might be a little bit clearer. The cooler colors are more lithogenic type lead, so more reflective of the natural sort of background lithology, the background rocks from which our local soils are derived. And the warmer colors are less lithogenic, more anthropogenic type isotopic composition. And we actually see, really excitingly, similar trends in other hive products. So we saw similar trends in the bee pollen we collected, as well as the foragers, the bee tissue. So for the last, I think, 10 minutes or so of this talk, I'm just going to go over a few applications that we've done using this idea of using honey as sort of a way to spatially visualize where metals may be distributed in various environments. And the first is that it's just kind of a cool map layer to play with. The database is public access. It's anyone can download it if you want to play with this data. It's been published, so please, I hope someone who understands a little bit more about how this could be applied in a more interesting way does something cool with it. But I've been playing a little bit with this idea. This is a vanadium nickel ratio is a concentration ratio that atmospheric chemists use to track emissions of heavy fuel oil. So the bunker fuel, which is the sludgiest, nastiest residue on the sort of spectrum of distillates versus residual oils, and that's what these tanker ships are burning. And wherever you see a lot of vanadium or a high vanadium nickel ratio is usually indicative of heavy fuel oils being burned. And I pulled, for fun, I pulled a paper from the UBC School of Public Health. They have this really nice index that factored in shipping density, wind factors, and nitrous oxide. And I just thought it was cool that these parallels sort of came through in the honey. Actually, pretty strikingly. So the second application is simply providing more context. So I looked a little more carefully at topsoil as a proxy for the resuspended particulate material that bees might be encountering. I also looked at PM10, and bees have, between their sort of mechanical mechanisms, so they're collecting pollen in a huge size fraction, but they also have these electrostatic forces that are working in their favor for collecting everything down to the ultrafine particulate range. So bees collect everything. And so I wanted to add a little bit more context to this. So I collected topsoil co-located with several of the hives. And I also dragged an air sampler around town at 3 different sites over the course of a year. There was one site at the Fairmont Waterfront Hotel, which is, you have a clean line of sight to both the Port of Vancouver and the, oh my goodness, the Canada Place cruise ship terminal. So right in the city center, we have a site at the Clark Drive Air Station, Metro Vancouver. Well, one of the chemists I met there affectionately called it Metro Vancouver's dirtiest sampling site because it's at the Clark and Broadway intersection, and it's stop and go traffic all day long, diesel trucks heading down and up the hill to the port almost all the time. And we had Site 3, which was the rooftop weather station at the Earth Sciences building. So again, here's the honey data on a 3-isotope plot. The city topsoil versus suburban topsoil versus rural topsoil was really interesting and actually matched the honey data pretty well in terms of lead sources. And so here we're looking at just the exchangeable fraction of lead in the topsoil. So this is excluding the lead that's bound in mineral or clay phases. And so that exchangeable lead has been deposited more recently. So it's more reflective of more recent activities and anthropogenic activities. And any anomalies, sometimes we could talk to the landowner or a park ranger and find out, oh, that topsoil has been amended. But in many cases, we don't know. We don't know the history of the topsoil, or if it's been moved, or if it was backfilled from a construction site. We don't know. So I was actually really shocked that this worked out so well. I have no idea if YVR has any influence, but I thought I'd point out that these 2 samples were from YVR, or near YVR. And this plot shows a lot, so we'll go through it slowly. We've got this sort of gradient fill is the honey data. So city honey is in red, and then the cooler color was the more rural honey. All the soils in brown. This is our global lead mixing line here. And then this dotted line is the Asian lead line, which is, it reflects just a different industrial history that some of the big urban centers there have, but it also reflects the Asian Loess Plateau in Central Asia and part of the Middle East, where we actually, those dust particulates make it all the way to the West Coast as trans-Pacific input to our particulate matter. So that's some context for you. And what I want to point out in the particulate, the PM10 data, is that the triangles that have the red outline, those were collected during the really bad 2018 forest fire season. It feels weird to say that because the 2021 was way worse. But but 2018, at the time that this was produced, was a really bad year. And you see a shift in the isotopic composition toward our local sort of background compositions. And in particulate matter collected on top of Whistler during 2 trans-Pacific events, we can actually see in lead isotopic space the difference, that input from the direct trans-Pacific input, or the direct trans-Pacific event that made it to the top of Whistler Mountain. So I think the takeaway message here is that the honey has a bit of a smoothing effect. So the nuance that appears in these other matrices, so the fires, the forest fires, and the trans-Pacific input in the PM, they don't necessarily come through in the honey. So that's an important consideration to make when interpreting this honey data. And that's, I think it's simply because we're sampling several environmental domains. So it's a bit of a holistic, I guess, sampling tool. So we had the unfortunate opportunity to witness last, gosh, was it, I guess 2 Aprils ago now, the fire at Notre Dame Cathedral. The rooftop and the spire are made of lead. There's loads of lead flashing, several hundred tons in between the roof and the spire. And the fire didn't get hot enough to completely volatilize the lead. It has to get really hot for that. It mostly just melted. So you can see here coming through a hole in the wall is melted molten lead oozing out. And the engineers that did the post-fire survey, they did sort of a back of the envelope calculation and realized that they knew how much lead was in the structure, and based on the amount of melted, resolidified, mangled lead, there were about 180 tons of lead unaccounted for. And we know that the fire got hot enough to release lead oxides as several different oxide dusts into the neighborhoods immediately downwind of the fire. And so we worked with a group, another urban apiary group they manage, oh my gosh, I think like 500 hives all across the greater Metro Paris region. And they were a great help in helping us get a suite of samples in July of 2019 post-fire. And they gave us some pre-fire 2018 Parisian honey as well for comparison. So here's a simplified version if this is too messy to look at, if this gives you a headache. But you can see that downwind of the fire, you have this sort of cone of higher lead concentration observed in the honey. And this footprint, this cone-like footprint, and then the decrease in excess lead was actually mirrored quite beautifully in a topsoil survey that was completed at the exact same time on over 3,000 samples through all of Paris. So that was pretty exciting and good news for us to support this. And it might be easier to view this way if you project all of this data onto a vector that follows the wind direction that night of the fire. You see here's the hive on Notre Dame's rooftop, and you see this big bump downwind of the fire. So in Paris, though, we did do isotopic work, but what was interesting is that the modern lead isotopic composition of Paris is really similar to the bulk of the lead, which is this is Rio Tinto ore from the Iberian Pyrite Belt that was used to build the current roof and spire at Notre Dame. And so if this fire had happened potentially in the 90s, this is the composition of the gasoline that they were burning, we probably would have seen a shift toward those Rio Tinto lead values. But this is interesting because it just shows you how important and how different the interpretation is in a city that literally has millennia-scale history of lead use. So the lead isotopes here don't readily offer leverage, but they do support the findings we see in the concentrations. And so for the final application I'll mention, we had a huge reliance on community science. And I was not expecting this, but people, after the first paper came out, people were writing us from all over the world because they were interested and they wanted to send us some honey from their backyard hives. And we ended up developing this sort of metal-free, really low-cost sampling kit that people could use. It's all really lightweight, so you could ship, I don't know, you could ship 30 of these in a box for really cheap, relatively cheaply all over the world. We have some community scientists, some sampling instructions in several languages, and we ended up with a huge suite of honey data. We actually have more in a freezer that I can't possibly get to while I'm here at UBC, but we ended up with just shy of 200 samples from all over the world. And a few key regions like New York City, we actually had a high school student collect about 60 honey samples for us. And she's a co-author on a paper in high school, which is phenomenal. So the community science reach here was really exciting, and for me, a really nice surprise. And so again, here's our global mixing line, our gasoline mixing line, and all of our samples fall rather predictively on it. So samples from the USA, plot down here in the more radiogenic region. That's because most gasolines burned in the US contained a lot of tetraethyl lead derived from that Southeast Missouri ore, whereas Oceania, Australia, New Zealand, and some European gasolines had a lot more of the Broken Hill or tetraethyl lead gasoline. And so this is mirrored in other consumables. So things like wine from Australia plot up here. And if you look at vinegars, cigarettes, other products, they all fall on that array depending on where they're from, assuming it's where they're actually from. There is a lot of issue with honey adulteration, and I think a lot of these products can be adulterated and sold as advertised as not from where they're actually from. And this also matches our modern global aerosol array as it stands today. So I have one more poll for you guys. This one's just to make sure you were paying attention.
There we go. And I will take this opportunity to remind you that we should be wrapping up, but I think you're probably close to doing that. Is that true?
Yes, yep. I think there's just a conclusion slide next.
Okay, perfect. All right, I'll end that, share the results.
Okay, I think people are getting the point. This is good. So yeah, all of these things are sources in Metro Vancouver. Metro Vancouver is not an old city, but it still suffered the effects of leaded gasoline, leaded paint, especially in downtown Eastside. There are a lot of repurposed brownfields that were previously used as just junkyards. It really, all of these things contain lead, and Vancouver is not immune to any of them. Although in general, Vancouver is a very, very, very clean city. I know a lot of you are aware of pretty decent air quality here as opposed to other places on Earth. I suppose when the province is not on fire. And so a brief summary, this data has some geospatial significance. The community science aspect is huge. People are already interested in honey and bees, which makes my job easier for outreach. It's like the hook is already built in for outreach. Sampling's low cost. These hive infrastructure exists everywhere, almost everywhere humans exist. So it's probably simpler to implement in other places as opposed to like an expensive network of air sampling that might require power, reliable power and security. And there is temporal significance of this data. We didn't talk about that today, but I'll just mention it here for you. And if you're interested in any more work like this, I would encourage you to check out either of these two research excellence clusters at UBC. Both of them have strong ties to community science. And I think actually probably a lot of you today are involved with this one, if not this one as well. So keep that in mind. And of course, this was a huge community effort, so I have a lot of people to thank.